So today we're going to continue on with the naming, and we'll be dealing with naming of acids and also naming of binary molecular compounds, and those mainly are just made of non-metals. Okay, so first up, naming acids. Now, of course, before we go on and saying when we're talking about acids, we should define what an acid actually is. And an acid, if we have here some generic formula, HX, and here X just represents the anion. When we add this to water, so this is when you're adding this to water, it will break apart into hydrogen ion plus whatever anion you actually have. So that's how acids actually operate. All right, now one other thing is when we have here the acid, the H is always going to be the first atom in the formula. Okay, so if we have the H afterwards, it's not an acid. So the H here has to come first, although when we see organic acids, that's a bit of an exception, but that we will cover when we get to that. But generally for these inorganic acids, the H here is always going to be coming first. The way we name these is, let's say we have here my anion, okay? So let's see, this is my anion I'm starting with, and we're going to make an acid out of that anion. So this is going to be my acid. If the anion ends in an IDE, this is going to become hydro blank ic acid. If the anion ends in an ATE, then it is just going to be the ic acid. And if it ends in an ITE, then it's going to be the OUS acid. So right here, this blank here just refers to whatever anion we're actually dealing with. So if I'm dealing with a chloride, that's going to become hydrochloric acid. If I'm dealing with chlorate, that's going to be chloric acid. If I'm dealing with chlorite, it becomes chlorous acid. Let's just write down a few examples just so this starts making a little bit more sense here. So we can show how this works with this example here. So notice here, my first one was the chloride. So there's my chloride. I add an H to the front of that, then I get hydrochloric acid. I start here with the chlorate. There's my 8. Now it becomes chloric acid. And then here my ClO2-, that's my chlorite. That becomes chlorous acid. All right, so that's just all the example that we had up there, how we actually use this. And just by the way, just as a little hint, knowing the difference between chloric acid and hydrochloric acid, very important. Nice little tricky test question, just a little heads up on that. So right here, there is a obvious difference between chloric acid and hydrochloric acid. Hydrochloric acid, this is a very, very common acid. It's used quite often in the laboratory. You can even buy this in the hardware store. It's commonly known as muriatic acid. And here's just a few other very common acids, and these are used quite often, and we will definitely be seeing these through the semester, and at some point you'll probably be even seeing these in your future lives as well. So here is the anion. So right here, nitrate becomes nitric acid, sulfate becomes sulfuric acid, phosphate becomes phosphoric acid, carbonate becomes carbonic acid. One thing to note here, all my anions, everything that we've written out here, these all have charges on them, either -1, -2, or -3. All the acids, there are no charges on these. There are no charges here, and these are neutral atoms, and these are neutral molecules. The other thing is, notice how many hydrogens we have. If you know the charge on all these anions, knowing how many hydrogens are in the acids is really, really easy. Okay? All the ones here that have a charge of -1, we simply add 1 hydrogen to them, and now we have the corresponding acid. If we have a charge of -2, we add 2 hydrogens. If we have a charge of -3, we have 3 hydrogens, and down here we have 2 hydrogens. All right, and that's the reason for this is, if we go back to our definition of the acid, here's our little anion. When it breaks apart, this is an H plus with my anion coming off as well. So down here, if I have a -2, I'm going to need 2 H pluses to make this a neutral molecule. For my phosphate, since that's a -3, I'm going to need 3 H pluses to make this a neutral molecule. Okay, so the number of hydrogens that we have in there is directly related to the negative charge of the anion we are actually dealing with. Okay, and these right down here, nitric acid, sulfuric acid, phosphoric, and carbonic acids, these are very, very common acids here. Okay, now we have here chlorite and chlorate. What happens if we have the perchlorate or hypochlorite? All we do is just add the per or the hypo to that one. I'll just write it out just for completeness here. So again, here's perchlorate becomes perchloric acid, hypochlorite becomes hypochlorous acid. Yeah, and also here we can even look, sulfide. This could form H2S, also commonly known as hydrogen sulfide, but if you form the acid, this can be known as hydrosulfuric acid. Okay, and just notice the difference between this and H2SO4, which is just sulfuric acid. So again, another great test question, the difference between hydrosulfuric acid and sulfuric acid. So just be aware of that. There's another category called organic acids, which we should look at. And these organic acids, they are also commonly known as carboxylic acids. And they have what's known in organic chemistry as a functional group, meaning that if you see this particular part stuck on a molecule, this gives it certain properties. And by the way, organic, just to remind everyone, means that it's a carbon-containing compound. So if we see this particular group in there, and it either look like this, COOH, or equivalently, C with a double bond OOH like this. Okay, so these are the two ways that we can see it. Now you might think COOH means that it's a carbon bonded to an oxygen, bonded to an oxygen, bonded to a hydrogen, but this is just a shorthand right here for this. So what you have to look for is, first of all, a carbon, and then it is double bonded to this oxygen, so you see two bonds right there. And then this is single bonded to an oxygen, which is then single bonded to a hydrogen. And right here, this is your acidic hydrogen. So when you add this to water, this is the hydrogen that falls off, and you make the acid that way. So for instance, acetic acid, which you may know more commonly as vinegar. Okay, so that's what acetic acid is. It's just plain old vinegar. And this is what acetic acid looks like. Okay, so this is acetic acid. And right here, what happens is you put this into water, and it breaks apart a little bit into, and actually this is because it's a weak acid. All organic acids are weak acids, but this breaks into like this. So this is acetic acid. This is what we call acetate, and of course that's just the hydrogen ion, and technically acetate ion. This can also be written out like so, just because this gets a little cumbersome, as CH3COOH, and we can write this as C. Okay, so these are exactly the same thing. This is just a more convenient way of writing it, just so it doesn't take up so much space. All right, and also if you happen to remember, we're looking right here, this is the acetate anion that was on this sheet. So that's what you can form acetate salts with these particular cations as well. So sodium acetate, copper acetate, calcium acetate, and so on. Now, one interesting thing about acetic acid and just kind of looking at how it forms in the body is, let's say you drink some ethanol. All right, so this is ethanol. It can also be written as CH3CH2OH, like this. Now, when you put it in the body, it reacts with an enzyme known as alcohol dehydrogenase. Now, this enzyme, alcohol dehydrogenase, oxidizes the ethanol and forms a new compound known as acetaldehyde. Also can be written as this. Now, since you are college students, you may be familiar with a concept known as a hangover. So if you drink large quantities of alcohol, even though you're not supposed to if you're under 21, this ethanol breaks down, is oxidized by the alcohol dehydrogenase enzyme, which pretty much everybody has, and then it forms this acetaldehyde, and this molecule right here is what gives you the hangover. All right, so that's that, headache feeling, whatever else you get. I don't have experience with that. But anyway, this acetaldehyde is what gives you the hangover. Now, this acetaldehyde undergoes further oxidation by a, there's other enzymes here, but basically it's oxidized some more. So there's some other enzymes and stuff that oxidizes. And then what happens is this forms the acetic acid. And then the acetic acid can be metabolized very easily in the body. And of course, that's why if you drink a lot of ethanol, you will gain weight, because it does eventually get converted into acetic acid, which your body does metabolize. So what you can see here, and if we start looking at these different compounds right here, which are the acidic hydrogens? Well, over here, all these hydrogens that are attached to just the carbon, none of these are acidic. The one here that's attached to an OH, and you can be like, oh, that looks very similar to this acidic H. But no, there's no oxygen double bonded to here, right? And also down here in this formula, there's no COOH. So this is not an alcoholic, or so this is not an acidic hydrogen right here. Also, you may be thinking, this OH, is that related to that hydroxide? No, this is bonded to the carbon. This is not related to hydroxides at all. So no, it's not a hydroxide. How about here with my hangover molecule, the acetaldehyde? Again, these hydrogens are not acidic. This one is attached directly to the carbon. It's not acidic either, even though there's this double bonded oxygen. So there's nothing acidic in this one. The only one that is acidic was the one that we showed before, which is this hydrogen right here. So that's your acid hydrogen. Okay, so that's the only one that makes an acid. Now, one other thing, and this is related to this. What you may be aware of is if you drink methanol instead of ethanol, that is very, very bad, because you can go blind and possibly die if you accidentally drink methanol. So why does that actually happen? So let's look at these molecules, and we can actually see what is actually so bad about this. So this is methanol, and you can see it's very similar to the ethanol molecule, except basically now I've just gotten rid of this CH2 group in the middle, right? So it's very similar to the ethanol molecule, okay? Even I just add an M in front of ethanol, I get methanol, right? Now what happens is the same alcohol dehydrogenase enzyme works on this molecule, because this enzyme, all it cares about is that there's this OH group on there. It doesn't care what the rest of the molecule looks like. All it says is, ooh, OH, I'm going to go and oxidize this molecule. And when it does this, it forms over here. This is what we call formaldehyde. Now, I'm sure everyone here has probably heard of formaldehyde. That's, of course, what they use to preserve dead bodies, tissues. When you have formaldehyde, that breaks down proteins and DNA, and of course, that's why it's very bad. And if you have large amounts of methanol or formaldehyde in your system, it will kill you. So this is why methanol is so poisonous. The methanol here is oxidized in the same way with the alcohol dehydrogenase enzyme to make formaldehyde. That formaldehyde builds up and poisons you. So it's not the methanol that's poisoning you, it's the metabolic byproducts which actually do the poisoning. So the interesting thing here is, and of course don't try this at home, if you do accidentally ingest methanol, please go to a doctor. But the way that the doctor is going to save you is what they call competitive inhibition. So what happens here is, let's say you drink a lot of methanol. Well, now this is being converted into formaldehyde. So what the doctor is going to do is give you basically a lot of vodka. And the vodka here, or the ethanol in the vodka, is going to keep this alcohol dehydrogenase enzyme busy making the acetaldehyde, and it's going to be too busy working on the ethanol and not have enough time to deal with the methanol here. And the methanol can just be expelled safely through the kidneys or through your breath or whatever. So the methanol leaves without being converted into the formaldehyde. So that's why the way that doctors save you is actually by getting you drunk on ethanol. So this way your body doesn't oxidize the methanol right here to make formaldehyde. All right, another one, and this is also closely related to this while we're on the theme, is ethylene glycol. So this ethylene glycol molecule, again, pretty similar to this one. It really doesn't matter where I put the OHs. Either they're up here on the side. They're all equivalent. You can see right here I have the OH group, this OH group. So it's what they technically call a diol. So it has two alcohol groups on here. So this is ethylene glycol. And when this gets oxidized, through the alcohol dehydrogenase, same enzyme. It's going to form this molecule. All right, and this is known as glyoxal. Not really important, but what actually happens here is that, again, this is further oxidized to the acid portion. So this is what's known as oxalic acid. And this is what poisons you, okay? So again, remember ethylene glycol, that's why you're not supposed to drink the fluid coming out of your radiator, even though it's supposed to taste very sweet, but it's poisonous. Because eventually what happens is this oxidizes in your body to oxalic acid. Now this oxalic acid here forms calcium oxalate, so something along these lines. So it forms this calcium oxalate molecule, and this is very insoluble. Okay, so essentially this calcium oxalate forms little crystals. They screw up your kidneys, and they form little crystals in your body, and it's all around bad news. Okay, so again, if you do happen to accidentally consume ethylene glycol, or even a bigger concern is your pets happen to be licking around your leaky radiator, the same way that the vet would save them, the same way that you save the person who has the methanol poisoning is by essentially getting them drunk with ethanol. So if your dog happens to lick up the ethylene glycol, you take them to the vet, they're going to give the dog vodka, or at least an IV of vodka, and again through the competitive inhibition, keeping this enzyme busy so it doesn't go and convert the ethylene glycol eventually into the oxalic acid, which is poisonous. Now on to the naming of these binary molecular compounds, and these are going to be the ones which are just dealing up here where they're all non-metals. All right, so we're not going to be dealing with before when we're dealing with these metals and anions. Now these are going to be molecular, meaning that they do not have cations and anions. They are just bound. They share their electrons cooperatively, and these are going to be the elements up here on this side with the non. All right, so there are a couple of rules here, because there's always rules in chemistry. So the first one, so the farthest element to the left in the periodic table is usually written first. So if we look here at the periodic table, that means that elements this way are written before the elements over on this side. One big exception here. So except for the oxygen, and the oxygen is always going to be last, unless you happen to be combining it with fluorine, and then the fluorine is going to take precedence over the oxygen. Now, why is this weird rule here? It actually has to deal with electronegativities, meaning that which elements actually do like the electrons the most. So fluorine is the most electronegative, followed by oxygen, then nitrogen. And the trend generally is that the elements over here like the electrons a lot more than the elements on this side. So that's why, and later on when we start seeing how we put these molecules together, we'll see that the elements on this side here are generally going to be the ones on the center atom, and the other ones are going to be the outer atoms over here. But we'll be seeing that later. But this is the general rule, that the elements over here to the left are going to be written first, except for the oxygen. Okay, now if we're dealing with atoms in the same column, the one with the higher atomic number, meaning the one that's lower down the periodic table, is going to be named first. So that means if we're dealing with something here like between silicon and carbon, it's going to be silicon carbide, not carbon silicide. Okay, so the one below it is named before the one above it. So that would be selenium oxide, not oxygen selenium, although the oxygen's always last anyway. But here that would be bromine fluoride, not fluorine bromide. Okay, so the one at the bottom gets named first. So the first element is just the name. You just have to write it down, copy from the periodic table. The second element, you're adding the IDE. So just like before, if we had the Cl, that would be chloride. So that's still going to be the same thing. So for instance, if I have here some sulfur chloride, sulfur you leave alone, and then the chlorine becomes chloride. Okay, and like I mentioned just a few seconds ago, silicon carbide, right? So silicon's the same, carbon becomes carbide. Not carbonate, but carbide. All right, so what you're going to do here is add this prefix, and we'll be covering that in a few minutes, which will tell how many atoms of each element are actually present. So we'll be seeing that in a few seconds. when we see these prefixes up here, the mono, which we're going to be seeing means 1, is never used on the first element. And the reason for that is there's a lot of elements that have one element in there, so it just gets a little bit redundant, so it just sounds a little weird. So the mono is just left off. But if it's on the second element, then you will use it. So that's why we have carbon monoxide, not monocarbon monoxide in that case, or carbon dioxide, but not monocarbon dioxide. Over here, if the prefix ends in an A or an O and the name of the second element begins with a vowel, then the A or the O is dropped. The reason for the second one here is basically when you have the name, it just rolls off the tongue much easier. So this is why we have monoxide, not monooxide, or pentoxide instead of pentaoxide. So it just helps the name roll off a little bit easier. If you happen to misspell it, I'm not really going to be too picky about this because, you know, spelling is not exactly everyone's strong suit. But this is just a rule, just to make it a little easier in the speech department. All right. So as for the prefixes, here they are. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. All right. So some of these you probably have seen before, so it shouldn't be too hard to think about what these terms actually mean. So mono, you know, everyone knows mono a mono, one-on-one, right? So mono, di, you know, we've seen that before when we talked about like diatomic molecules. That just means there's two atoms in the molecule here. Tri, you've probably ridden a tricycle at some point. You know that has 3 wheels, so the 3 in there. Tetra, tetrahedron, right? You've probably seen that in your math class. So of course that means that there's 4 sides on there. So that's the 4. Penta, think of the pentagon, right? That has the 5 sides on it. Hexa, that's 6. Probably have seen that at some point, I would say. 7 for hepta. That one's probably the one that you have to worry about actually memorizing, because especially here, the hexa and the hepta, they sound really close. Hexa, hepta, so you know, just make sure you don't goof up these. Hexa is 6, hepta is 7. Octa, think of octagon, octopus, right? 8, so that comes up very often. 9 for nana, that one we really don't see too often, so you just got to memorize that one. And then 10 for deca, think decade, right? That means 10 right there. So you know, these aren't too hard. And the nice thing is when we're naming these, as opposed to when we were dealing with the ionic compounds where we have to deal with the charges, these just simply tell us how many atoms are actually in that particular molecule. So what we will do is use these prefixes right here to form some molecular names. All right, so here is ClO2. And just notice that all these things we're going to be dealing with here are all composed of non-metals. So ClO2, so this is 2 chlorines, so that's why it's dichlorine. And then here I just have 1 oxygen, it's monoxide. Again, here's the nitrogen. Now there's no mono here, because remember the mono doesn't apply if it's on the first element, so we don't need the mono right here. So this is just regular old nitrogen. And then of course I have 3 fluorines, so this is going to be trifluoride. So again, here I have 2 nitrogens, so this is dinitrogen, and then I have 4 oxygens, so this is my tetra, so this is tetroxide. Notice I just dropped the A here in regards to this rule over here, just to make it easier to roll off the tongue. If you happen to write tetraoxide, that's fine. I'm not going to be too picky about that, but just remember that this is just so it's a little bit easier to spell. So P4S10, so that's tetraphosphorus decasulfide. All right, so there's my deca for the sulfur right there. ClO2, there's chlorine, again, no mono because it's the first one, and then dioxide, okay, because I have 2 oxygens with the IDE. So one important point is with these binary molecular compounds, and just notice from the word, binary, meaning that I'm going to have 2 elements in here, and then these are molecular compounds, so there's no ions or anything in these. For these compounds, if I just tell you that, you know, this compound has chlorine and oxygen, or nitrogen and oxygen, or phosphorus and sulfur, or something else, there is no way for you to know what the formula actually could be. Now, if I'm dealing with an ionic compound and I tell you you have a nitrate and calcium, right away you should be able to figure out what that formula is, because if we're going back to the sheet here, where's my nitrate? Yeah, for my nitrate down here, and there's my calcium, it can only be this compound. Okay, but if I'm dealing with these binary molecular compounds, I can put these in a multitude of different combinations to get it out. And there's no way to know if you just have nitrogen and oxygen what your actual compound will be, because like just for nitrogen and oxygen, there's like a half a dozen different possibilities here. So you need to, either have the formula or have the name to be able to get the other one there. And then we can also go backwards on this as well. So let's start with the name and figure out what the compound actually is. So sulfur hexafluoride, so my sulfur right there. And then notice I have here fluoride, okay, F, and hexa means 6. So that's SF6. Carbon, there's my carbon. And then I have an oxide, so that's the O, and then I have 2 of them, CO2. And another one that everyone's probably heard of, carbon monoxide, carbon with an oxygen. And again, these are 2 very different compounds. Carbon dioxide, you exhale this, every day, no problem. Carbon monoxide, you inhale this just a little bit and it can kill you. So, these, one little oxygen difference between these result in very different properties between these molecules. Okay, we can also look here. Let's say I have dinitrogen trioxide. So I have here N, and I have 2 of them, and then my oxygen, and I have 3 of them. So you can see right here, we've already covered, we have this one over here, dinitrogen trioxide. We have this N2O3, dinitrogen trioxide here. So, like I said, there's a lot of different possibilities for this. Okay, now here we have dihydrogen monoxide, a very scary sounding molecule, but here we have H, that means we have 2, and 1 oxygen, which of course is our friendly water molecule. Okay, so one thing they always have a lot of fun with to see for science illiteracy in the general populace is go around and have people sign a petition to ban dihydrogen monoxide, and of course people sign it because they don't realize that that's just the scientific name for water. Now there are certain molecules which have special names for historical reasons here. So of course we have H2O, which is of course water. Yeah, CH4, which is methane, and if you happen to look right here, methanol, that's where methanol gets its name, is its derivative of methane. So that's why it's called methanol. And ethanol, by the way, is a derivative of ethane. Another one here, and there's also, well, this isn't used quite so often, but it's kind of interesting. This is called silane. So this is the silicon version of methane. Oh, and by the way, methane, this is natural gas. So if you have a gas supply for your stove or for your heat, this is methane which comes through the pipes. Of course, if you're not connected to the natural gas network, you probably might use propane. That's another hydrocarbon related to methane there, but it's just a little bit longer in terms of its length. But also, methane does not have any natural smell. Okay, what they have to do is add an odorant to the methane to actually give it its natural gas odor, because otherwise people wouldn't know there's a gas leak and houses would be exploding. Here's another one. So NH3, this is ammonia. And I mentioned this earlier, this is not the same as ammonium. These are different. Ammonium, this is the protonated version of ammonia. Okay, so these are very different molecule. Well, one's a neutral molecule, one is an ion, of course. And we can also have here pH3, which is known as phosphine. This is really, really poisonous. You don't want to be anywhere near that. Now, like I said earlier, these compounds, when we're dealing with all the naming and everything, they can have multiple possible combinations of elements in there. However, if you're dealing with a hydrogen compound, so you have hydrogen bonded to some other nonmetal, there's actually only one possibility. So if we look here at the periodic table, basically the hydrogen will bond once. In other words, all these compounds right here will have 1 hydrogen. All these compounds here will have 2 hydrogens. All these compounds here will have 3 hydrogens. All these compounds here will have 4 hydrogens. And really, that's as far as we're going to worry about going. But this is going to make our lives a lot easier trying to figure out what the formulas are for these. And actually, we already saw some. Ammonia and phosphine, NH3, pH3. Water, H2O, and for the sulfur, that's hydrogen sulfide. That's going to be H2S. Hydrogen selenide, H2Se. Hydrogen telluride, H2Te. And over here, HF, HCl, HBr, HI. Okay, all of these have the hydrogen, only one of them. Another thing, when we're writing out these formulas, everything in this row has the hydrogen first. Actually, that makes all acids, hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic acid. Over here, the hydrogen also goes first. So that's H2O, H2S, H2Se, H2Te. On this one, now it reverses. The hydrogen goes second. So that's NH3, PH3, ASH3, SBH3, all of these have the hydrogen afterwards. Same thing over here. That's why it's CH4, SiH4, GeH4, SnH4. So all of these have the hydrogen last, these have the hydrogen last, these have the hydrogen first, and these have the hydrogen first. Okay, so that's the important thing right there. And because of this, since all of these here can only have one possibility, that's why if we're naming these compounds, let's say H2S or HCl, these will be hydrogen sulfide, not di. You might think, well, this should be dihydrogen sulfide because I have two hydrogens here, but when you're dealing with a hydrogen, it's always going to be H2S. You're never going to have an HS or H3S. It's always just going to be H2S. Same thing down here with the HCl. Now, of course, we know this as hydrochloric acid. So we know this as hydrochloric acid, but this can also be called hydrogen chloride. So it's hydrogen chloride, or hydrogen monochloride, because again, it's always going to be HCl. It's never going to be H2Cl. It's always just going to be HCl in that case. All right, now you might be wondering, well, why are there two different names for the same compound? The hydrochloric acid. So the hydrochloric acid is when you take the hydrogen chloride gas and dissolve it in water. Hydrogen chloride is when you just have the pure stuff just in the gas form. Okay, so there's a little bit of ambiguity there, but if you're dealing with anything that is an acid, it's going to be dissolved in water. If you're just dealing with a tank of hydrogen chloride, it's going to just be the gas. Now, of course, if you were to inhale the hydrogen chloride gas, that would be very bad because the hydrogen chloride gas will go into your lungs, react with the water in your lungs, and make hydrochloric acid, and of course start dissolving your tissue, and many, many bad things actually happen there. And again, just to help you with your studying, this is that same handout we saw earlier. Here we have all the lists of the acids according to the rules. So I have listed here the halogen acids, and of course we add 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. So hopefully by looking at the patterns with all this, this will help when you're actually naming these compounds here. And then the next page, these were those common molecules that I was mentioning. Here's hydrogen chloride, hydrogen bromide, hydrogen iodide, methane, ammonia, water, of course, silane, phosphine, hydrogen sulfide, methanol, ethanol, acetic acid. So these have common names, not exactly conforming to the usual rules we were talking about for the binary molecular compounds. And here we have summarized the prefixes for the binary molecular compounds. And I just want to point out right here that I have in bold, these are to be used with molecular compounds only. In other words, 2 nonmetals. Okay, you do not use these when you are dealing with cations and anions. All right, if you have an ionic compound, you do not use these. So for instance, it would always be aluminum chloride, never aluminum trichloride, or lead tetrachloride. It's would be lead for chloride. That's it. You do not use those prefixes if you're dealing with the with the metals. Also is very important. So like right here, N2O, dinitrogen monoxide, Cu2O, that's copper 1 oxide, not dicopper monoxide. So again, make sure you got that straight. And then over here, these are just some examples with the binary molecular compounds. Again, not all inclusive, but hopefully enough practice ones to give you a heads up. And also right down here, noting the difference between sulfur trioxide and sulfite. The charge on these ions, if they are an ion, is very important because if you leave the charge off, that could be a molecular compound. They could have the same formula, but one is charged and the other one is neutral. All right, so it is very important to know the difference. Right here, nitrogen dioxide, that's NO2. What we saw earlier, nitrite, is NO2 minus. Okay, that little charge makes all the world of difference. We have here a gas. We have here something that forms an ionic compound. Look through these. We'll be doing definitely some practice with these in class, but look over this as much as possible, and hopefully this will be of some use to you. All right, so I think I've said enough with this, so I will stop it here.